Welcome viewers. In this video we'll see the magnetic potential. There are two types available: scalar magnetic potential and vector magnetic potential. First we'll see the scalar magnetic potential. It is denoted by U. Scalar magnetic potential by the symbol is U. So we know that the E equal to minus del V. The relation between E and V, electric field intensity and potential, is E equal to minus del V. The del is nothing but the partial differentiation x, y, z. If it is rectangular coordinate, x, y, z. Similarly, for magnetic potential is given by H equal to minus del U. Here E is replaced by H, V is replaced by U, right? So if we consider this is for electric field, if it, in case of magnetic field, the same thing is given as H equal to minus del U. Now take curl on both sides. While taking curl, what will happen? Curl H equal to minus curl of del U, right? The curl H equal to minus curl of del U. That is nothing but curl H equal to minus curl. This del U is nothing but gradient U. The del U can be replaced by gradient U. But we know that curl H equal to 0. Curl of H equal to 0. But according to Ampere's law, curl of H equal to J, current density, right? So the normal derivation, normal expression, curl of H equal to 0, but based on the Ampere's law, the curl of H equal to J, right? These two are not matching together. So from the above relation, the Maxwell's concluded that the concept of scalar magnetic potential is applicable only for magnetic field produced by permanent magnets, right? So the scalar magnetic potential is applicable only permanent magnets, not a electromagnet, right? So the Maxwell's concluded that these relations are applicable only for permanent magnet, not a electromagnet. So this concept cannot be applied to the field produced by steady current. That is not possible to apply for the permanent magnet. Can be applied, not a electromagnet. Cannot applied for electromagnet produced by steady current. So from that, what we can conclude? We know that integral E dot EL equal to V. Similarly, integral H dot equal to U, the scalar magnetic potential, right? But according to Ampere's law, integral H dot dl equal to I, right? So based on this, integral E dot dl equal to V means H dot dl equal to U. But Ampere's law gives H dot dl equal to I. So by comparing these two, these sides are equal, integral H dot dl. So these two expression in these two sides also equal. So that U equal to I. That is scalar magnetic potential is equal to current, right? So we can represent scalar magnetic potential is nothing but a current. So that is given here. The unit of scalar magnetic potential is amperes, right? So we conclude that U equal to I. The unit is amperes. Now we'll see the vector magnetic potential. So vector magnetic potential is denoted by the term A. What is vector magnetic potential? The dA. The A is the magnetic potential. dA means magnetic potential due to small length L. L is the length, small length dl. So due to that, the magnetic potential, vector magnetic potential, become dA. So that is, so the dA is the magnetic field potential due to the current element IDL. Current element is nothing but I into dl. That already you know that. So due to this current element, the magnetic field intensity is dA. So this dA is proportional to IDL and inversely proportional to distance r. The distance between the ideal and point P is r, right? So this dA is directly proportional to ideal vector and inversely proportional to r, distance between the point and current element. So while equating, we introduce one constant, that is mu by 4 pi ideal divided by r. So the dA can be expressed as mu by 4 pi ideal by r. So this dA is the magnetic potential, vector magnetic potential only due to small element ideal. So by integrating on both the side, we will get the total vector magnetic field. Now we can refer this diagram. So this is the current element I. Here this is the conductor. The current is flowing through this conductor. Here n number of current elements available. We consider one current element ideal. We need to find what is the magnetic vector magnetic potential at this point P, which is at a distance r meter. Right. So due to the small current element dl, we represented as magnetic potential as vector magnetic potential as dA. Right. So this is the conductor available. The current is flowing through the conductor. Magnetic field is produced. This conductor is assumed to be having so many current elements. We consider only one current element. The magnetic potential due to this current element at point P is dA. This point P is located at a distance r meter. So the magnetic field intensity magnetic potential due to entire conductor can be obtained by integration. So integral, this expression is available. By integrating this, we will get the total vector magnetic potential. So integral dA equal to integral mu divided by 4 pi ideal vector by r vector. So integral dA is nothing but A, that is equal to mu by 4 pi, integral mu by 4 pi ideal vector divided by r. Now for the simplification, multiply and divide with the term area A. Right? We are going to multiply and divide by the term A. So what will happen? So A vector equal to integral mu divided by 4 pi ideal vector divided by r into A divided by A. So the originality will not affect. Area, the term area, A by A. So it is rewritten as A vector equal to mu by 4 pi is constant, that is taken outside. Integral I by A, we are combining these two parameters, I by A into dl divided by r. Right? So this I divided by A is written here, dl A written here, and r is written here. What is I by A? Current by area, that is nothing but current density. What is A into del? Area into length, that is nothing but volume. Right? I by A is nothing but the current density. Current per unit area is nothing but current density. Area into length is nothing but volume. So that A vector, the vector magnetic potential equal to mu divided by 4 pi integral J current density, J dot dV volume divided by R. So this is the final expression for vector magnetic potential. So in this video we discuss about the magnetic potential, the two types, scalar magnetic potential and vector magnetic potential. Thank you.